Hello everyone. Let me walk you through the highlights for this unit, and we're going to continue to talk about heat. Specifically, how an object is going to change when we add heat energy to it. And the first equation we have here is Q equals mc delta T. Q is the symbol that we're going to use for the energy added to an object. It's going to be in joules. M, of course, is the mass of the object. C is a new term for specific heat. I'll talk about that in a second. And delta T, this is how much temperature the object is going to change when you add energy to it. Now, specific heat, this is how easily a substance is going to change temperature with energy. So if I add the same amount of energy to sand versus the same amount of energy to water, the sand will change temperature differently than the water would. This is also true for any other objects like, steel, gold, aluminum. Also, different phases of objects are different. So the specific heat of water is different than the specific heat of ice. Now, a lot of these are tabulated in your book, but I'll give you these in the problems when you need them. Let's do one of those now. So here we have a pot that contains 2 kilograms of water, and it absorbs 25,000 joules of thermal energy from the stove. I want to know, how does the temperature of the water change? How much does it increase by? And so I give you the specific heat capacity of water to be 4,186 joules per kilogram Celsius. So we use our equation. The energy added, Q, is 25,000. The mass of our water is 2, and the specific heat of water is 4,186. And then we want to solve for how much temperature the object is going to change by. So we arrive at 2.99 degrees Celsius, and so pretty much 3 degrees. So the water has increased by 3 degrees now. But what happens when we start to reach the boiling temperature? If I add more energy to the water while it's boiling, what's going to happen? So let's talk about that next. And we do this with this plot here. So the vertical axis here is temperature of our object, and the horizontal axis is how much energy I've added. So let's start down here at the very bottom left. So we have a block of ice that's negative 50 degrees Celsius. As I add energy to the ice, let's say I'm heating it up on a stove or something, okay? As I add energy to it, the temperature of the ice is going to increase up until we reach 0 degrees Celsius. At that point, the ice is going to start to melt. Now, something strange starts to happen. As I add energy to the ice temperature will not increase anymore. It's only going to turn that ice into water. So, the extra energy needed is to melt. There's extra energy needed to melt the ice, and this is called the latent heat of transition. And we have a whole new equation for that. Q, the energy needed to transition an object from one phase to another, is equal to the mass of the object times the latent heat L. Okay, and this is going to be different for different substances. It's also going to be different for different phases. So there's a different latent heat to go from a solid to liquid, and a different latent heat needed to go from a liquid to a gas. So here is an expanded plot of what I just talked about. So in the bottom left, that's what we did before. We took that negative 50 degrees Celsius ice and we warmed it up and started to melt it. So when we add energy to ice when it's below its melting point, it's going to increase the temperature of ice until it reaches its melting point, which is 0 degrees Celsius. Then once it's at 0 degrees Celsius, any energy that I add now is only going to turn that 0 degrees Celsius ice into 0 degrees Celsius water. And it's going to do that up until all of the ice has been fully converted into water. Then, once it's fully water, when I add energy to the the water now, it's going to increase the temperature of the water. So we go from 0 degrees Celsius water, adding energy is going to keep increasing the temperature all the way until all of that water is at 100 degrees Celsius, the boiling point of water. Now, when I add energy to this water now, it's only going to change the water from being liquid to being a gas, to being steam. It's not going to increase the temperature of the water anymore. So energy added turns 100 degrees Celsius water into 100 degrees Celsius steam. It's going to keep doing that all the way until all of the water has been converted to steam. And now when I add energy to the steam, it's going to increase the temperature of the steam. So there's a lot of different phases here. So adding energy when you're in between the melting and freezing points, it's only going to increase the temperature. And then when we're at those boundaries, then it's not going to increase the temperature anymore. You need energy in order to convert the object from one phase into another. Let's do another example. So let's say we want to melt 1 kilogram of gold. How much energy would this take if the gold starts at room temperature, so 20 degrees Celsius? Here I give you some information about gold. It melts at 1,063 degrees Celsius. The specific heat of solid gold is 129, and the latent heat of fusion is 64,500. This is the latent heat to go from a solid to a liquid. And so let's first figure out how much temperature that we need to increase it by. So let's find that delta T. That's the final temperature minus the initial temperature. Well, the final temperature is 1063, and the initial temperature is 20 degrees Celsius, so we can just plug those in. So we want to increase the temperature of gold by 1043 degrees Celsius. With this, we can plug this into our heating equation, Q equals mc delta T. So because this isn't at the melting temperature yet, we've got to calculate how much energy it takes to warm it up to the melting temperature. So we can plug in our numbers here. The mass is 1 kilogram, the specific heat is 129, and we want to increase it by 1043 degrees Celsius. So we arrive at an energy of 135 kilojoules. That's how much energy needed to raise the temperature to the melting point. But then to calculate how much energy to fully melt it, we need our other equation, the latent heat of transition equation. So Q equals ml. And I put a little subscript m here for melting. So the energy needed to melt the gold is equal to the mass of the gold times the latent heat of fusion, which I tell you here, 64,500. And so we arrive at an amount of energy of 64,500 joules, or 64.5 kilojoules, because the mass is 1 kilogram. Now, the total energy needed, that's both of these together. So we needed to add energy to raise the temperature, and then we had to have more energy in order to convert it from a solid into a liquid. So the total energy is those two numbers added together, and we arrive at almost 200 kilojoules of energy. Now, a bit of a follow-up question. If our furnace applies heat at a rate of 70 watts, how long does it take to melt the gold? So if you recall, power is work over time. Now, work is just the transfer of energy from one form to another. So we want to transfer 199.5 kilojoules of energy. So that's what we're going to plug in here for our work, Q. We want to solve for T, the time it takes to do this. So we can multiply T to both sides and divide power to both sides. And then we plug in our numbers, and we get 199,500 divided by 70, because that's the power in watts. And we arrive at 2,850 seconds, or around 47.5 minutes in order to fully melt the gold. For this part of the unit, we've really only added two equations. The energy required to warm an object, Q equals mc delta T, and the phase transition equation, Q equals ml. So you need to think about which one you're going to be using. So when you're warming an object, you use this one. And then when you're undergoing a phase transition, you use this one. All right, I hope this helps. Let's get started.